Hello guys, welcome back to my YouTube channel. So today I'm going to start off with a new topic, Introduction to VLSI Fabrication. VLSI or Very Large Scale Integration is the process of creating complex electronic circuits by integrating millions or billions of tiny components onto a single semiconductor chip. The fabrication of VLSI circuits involves a series of intricate steps that transform raw materials into functional high performance integrated circuit. So this was all about a small introduction to VLSI fabrication. Next slide, we have the wafer preparation. Step 1 is wafer slicing, surface polishing and cleaning. Wafer slicing, cutting silicon ingots into thin wafers. Surface polishing, smoothing the wafer surface to atomic level flatness. Cleaning, removing impurities and contaminants from the wafer. The VLSI fabrication process begins with the preparation of silicon wafers. First, silicon ingots are sliced into thin, round wafers, typically 300 to 450 mm in diameter. These wafers then undergo a miscellaneous polishing process to achieve an extremely smooth, mirror-like surface at the atomic level. Finally, the wafers are thoroughly cleaned to remove any residual impurities or contaminators, ensuring a pristine surface for the subsequent fabrication steps. So this was all about wafer preparation. Next slide, we have the photolithography. It involves wafer preparation, applying photoresist, exposure and development, and etching and removing photoresist. Wafer preparation. The fabrication process begins with a highly polished silicon wafer free of any defects or impurities. This wafer serves as the foundation for the entire integrated circuit. Applying photoresist. A light sensitive polymer called photoresist is then coated evenly across the surface of the wafer. The photoresist acts as a mask to selectively expose or protect specific areas of the wafer during subsequent processing step. Exposure and development. The wafer is then exposed to a specific pattern of high energy light, typically ultraviolet radiation. This exposure causes a chemical change in the photoresist, making the exposed area either more or less soluble depending on the type of photoresist used. Etching and removing photoresist. After exposure, the wafer is immersed in a chemical solution that selectively dissolves and removes the exposed areas of the photoresist. This process transforms the desired patterns from the photo mask on the wafer surface, which is ready for the next fabrication step. Next, we have the thin film deposition. Physical wafer deposition, chemical vapor deposition, atomic layer deposition. Physical vapor deposition. Atoms are ejected from a solid or liquid source materials and deposited on the substrate. Chemical vapor deposition. Atoms are formed by chemical reaction and then deposited on the substrate. Atomic layer deposition. Atoms are deposited one atomic layer at a time in a self-limiting process. The film deposition is a critical step in VLSI fabrication where layers of various materials such as metals, insulators and semiconductors are deposited on a silicon wafer. This allows the creation of complex integrated circuits with intricate patterns and structures. The choice of deposition technique depends on the specific material, desired film properties, the manufacturing requirements. Each method has its own advantage and is usually selective throughout the fabrication process to build the final integrated circuit. Next, we have the etching. Etching has three steps mainly: masking, wet etching, and dry etching. Masking. The first step in the etching process is to apply a protective mask to the wafer surface. This mask, typically made up of photoresist material, defines the area that will remain after the etching process. Wet etching. In wet etching, the wafer is submerged in a chemical solution that selectively removes the unmasked material. This technique is often used for large-scale removal of materials like silicon or metals. Next, dry etching. Dry etching is also known as plasma etching, uses a gas phase chemical reaction to remove materials. This method is more precise and can achieve higher aspect ratios, making it suitable for creating intricate features on the wafer. So this was all about etching. Next, we have the doping and ion implantation. Impurity doping, ion implantation, activation and annealing. Impurity doping, introducing controlled impurities into semiconductor materials. Ion implementation, accelerating ionized dopant atoms into the semiconductor lattice. Activation and annealing, thermal treatment to activate and distribute the dopants. Doping and the ion implementation are crucial steps in the VLSI fabrication process. Impurity doping involves introducing controlled amounts of dopant atoms such as boron or phosphorus into the semiconductor materials to modify its electrical properties. Ion implementation is a more precise technique that accelerates ions dopant atoms and embeds them directly into the semiconductor lattice. After implementation, an activation and annealing step is performed to distribute the dopants and restore the crystalline structure of the semiconductor. So this was all about doping and ion implementation. Oxidation and diffusion. Thermal oxidation, doping and diffusion. Thermal oxidation. Silicon wafer is exposed to high temperature oxygen to form a protective silicon dioxide SO2 layer. Doping. Impurities are introduced into a silicon wafer to create desired electrical properties. Diffusion. Dopants are then driven deeper into the silicon through high temperature annealing, creating precise device junctions. Oxidation and diffusions are critical processes in VLSI fabrication as they enable the creation of essential device structures and electrical characteristics. The thermal oxidation step forms a robust insulating layer while doping and diffusion precisely control the semiconductor properties, laying the foundation for complex integrated circuit. This technique precisely tailors the material properties at the atomic scale, enabling the miniaturization and high performance of modern microelectronics. So this was all about oxidation and diffusion. The metallization. It involves deposition, patterning, and multiple layers. Deposition. The metallization process begins with the deposition of a thin metal film typically made up of materials like aluminum, copper, or tungsten onto a semiconductor wafer. This metal layer serves as the interconnection between the different components on the integrated circuit. Patterning. After the metal film is deposited, it is patterned using a photolithography technique to create the desired interconnect designs. The unwanted metal is then removed through a selective etching process, leaving behind the precise metal traces needed for the circuit. Multiple layers. In modern VLSI fabrication, multiple layers of the metal interconnections are used separated by insulating dielectric layers. This allows for more complex and dense circuit as the metal layers can cross over each other without causing short circuits and interference. Packaging and assembly. Wafer dicing. The fabricated wafer is carefully cut into individual chips or dies using a precision saw or laser. This process is known as wafer dicing, separates the functional components on the wafer into manageable units for further processing. Die bonding. The dies are then mounted onto a substrate such as lead frame or a printed circuit board PCB using a conductive adhesive. This process is called die bonding. Securely attach the die to the package base, ensuring a strong mechanical and electrical connection. Wire bonding. Thin flexible wires are used to create electrical connections between the bond pads on the die and the corresponding leads on the packages. This wire bonding process establishes the critical path for electrical signals to flow between the integrated circuits and the outside world. Now we have the challenges and the future trends in the VLSI fabrication. As the semiconductor industry continues to push the boundaries of miniaturization, VLSI fabrication faces a range of formidable challenges from maintaining Moore's law to addressing power consumption and heat dissipation. The road ahead is paved with complex technical hurdles. However, cutting-edge innovations in materials process and designing offer promising solutions that will shape the future of the high-performance computing. So this was all about today's topic. If you like today's topic, please like, share and subscribe to my YouTube channel. Thank you.